Yeah, it is kind of blurry, but like the top line is like Social Security, the next one's health, income security, then national defense, then Medicare. But most of what the government does, most of what our federal government does is a money transfer pipeline. So you think about like the Social Security program, you can think of it as, if you thought of it as software code, essentially what you're doing is you are taking a fixed percentage of everyone else's income, and then you are putting into a big pool and then paying it out to other people. And like that's the single largest function that the US federal government does, and it would be relatively easy to turn that into code. You could imagine that there's like, if everything is being conducted on a blockchain, you could imagine transaction fees being taken out on like each like market transfer on economic purchases, and then that is placed in a fund, and then other people draw from that fund as needed for like income security and stuff. So that's kind of like the idea of the future that I feel like blockchain is working towards, and I feel like that's why like everybody's here. That's why ETH Denver, and it's not just to try to get rich and make some shit coins and flip them really fast and stuff. There's plenty of that, but that's like the long-term goal of why anybody should care about blockchain anyway. So today I wanted to, blockchains aren't doing too great right now because they're not super secure, and the incentives of the people running them are not very well aligned with like a societal future, a good societal future. Obviously, so like these are some of the top hacks. Mostly in Solidity, because like most of the liquidity is in Solidity, or I should say most of the locked TVL, total value locked, is in Solidity smart contracts right now. So it makes sense that they're the most hacked, but it's also really hard to write secure Solidity code. For those of you not familiar, Solidity is the programming language of Ethereum. And there's a lot of really smart engineers who spend a lot of time like working very, very hard at making sure their contract is secure, and they still get hacked. So you can see that, I don't know, there's like a couple $1 billion right there on that leaderboard. That was from last year getting stolen. I mean, the second biggest one was just SBF stealing everybody else's money again on the blockchain. So let's see. So I don't believe that the Ethereum virtual machine, is it's the execution environment in which Solidity runs. And then Solidity is the programming language in which smart contracts are written on Ethereum. And I don't really believe that any of that is going to be the future, simply because the EVM is inefficient and does not scale. And by that I mean that you cannot run processes concurrently on Ethereum in the sense that like every transaction needs to be executed serially, and you can't split them and run them in parallel. So you can't take advantage of like multiple cores, for example. That's what I'm talking about on the base layer one. Feel free to, if anybody has any questions and stuff, just raise your hands and stuff. I'm happy to be interactive. There's not many people here, so we can make this like a pretty cool conversation. Also, Solidity itself is insecure. Like I said, it's really hard to write solid code. And the next is like, the big thing right now in Ethereum that you're gonna hear a lot about this week, I'm sure, is like layer 2s. So layer 2s, the concept is pretty cool, but the problem is it bifurcates liquidity too much. So you can imagine you have 10 different layer 2s. Coinbase just announced their own layer 2 2 days ago, actually. So the problem is that when you bifurcate your liquidity, it takes a long time to move things around. So you could imagine that you're on Optimism, and then you're on Arbitrum, and then you're over on Coinbase's new thing, and like none of us can like send money to each other or really talk to each other unless we're all on the same network, right? We have to go from Arbitrum to back to Ethereum, then to Ethereum, back to Optimism, etc. It bifurcates things a lot, and it takes a long time to withdraw money from it. So Optimism, it takes 7 days to withdraw money from it, which is like very slow in block, even in bank terms, it's very slow. And that's fundamental to their security model. It's not sort of a technical limitation that can be really improved. So the ideal future that we're trying to work towards is a safer programming model, which is mostly what I'm going to be talking about today. And then faster parallel execution. If you could take advantage of multiple cores when you're in your execution environment, that'd be great. And then you need a network that scales without breaking atomicity. Yeah. So that's why I introduced Dogecoin. No, just kidding. That's why I introduced SWE. Right now SWE is in testnet 2. We just finished testnet 2. To give you a little bit of history on SWE, it was started by the, first of all, I don't work for SWE. I just work with SWE on like an NFT kind of standard thing. So SWE was started by Facebook engineers at the beginning of 2022. They left Facebook after Diem fell apart. So, yeah, well, I'll get to Diem. They left Facebook after Diem fell apart, and then they started their own blockchain called SWE. They managed to raise around 300 million from like the A16Zs, FTX, before FTX collapsed, types. Yeah. So, but before we talk about all that, I want to talk about the Move programming language, the Move programming model rather. Move is a new type of language, smart contract language. It's a very smart contract specific language, and I call these resource-oriented programming languages. And resource-oriented programming languages, the idea is that you have this globally shared like type system, and that objects can move around between modules. So in Solidity, you have every smart contract is essentially like a table or like a hash map, and you map objects to like map for an NFT implementation. You would map the object ID, or rather the NFT ID, to like an owner. And so then you have a bunch of functions that set that or get that value. None of the contracts in Solidity understand each other unless they are programmed to understand each other, in the sense that like you're just passing data that you have to serialize and deserialize. And it's the same way in Solana. So Move I'd say is the most successful resource-oriented programming language in terms of like adoption so far, which isn't saying much because there's very few Move developers. But Move exists on Diem and SWE. So Diem was Facebook's blockchain. They started as Libra. They turned it into, then they rebranded it to Diem. They started back in 2018. They started researching in 2018, announced it 2019, killed it at the beginning of 2022. Yeah. There's also Cadence, which is the programming language of Flow. If you guys are familiar with Flow, does anybody know what Flow is? A few people? Okay, yeah. It was like CryptoKitties. The CryptoKitty guys made their own blockchain, and it's the blockchain itself kind of sucks, but like Cadence as a programming language is pretty cool. There's also this like really obscure language called Scripto by this other blockchain that's pretty obscure called Radix that isn't out yet either. Yeah. So it'll make a little more sense once we get into it. So I wanted to show, this is a breakdown of a Move module. And I want to explain how like incredibly simple Move is. It's a very, very, if you guys are from Rust, this is like a fifth the complexity of Rust. So this is like a Move module right here. You can't probably see it the best, but at the top you can see that there's a module declaration, and it says module SWE examples and then BUIDL week is what it'll say. So what that's saying is that you're declaring a new module. You have an address called SWE examples. So, and then you have like addresses are where there are unique identifiers that exist globally. They're globally unique identifiers by which you find things. So every object that you publish will get an address, and those are just like 32 byte. I wonder if I can zoom in and like show this. Maybe not. They're like these 32 byte little like hash things. They represent, in SWE, they represent them as, well, they're 20 bytes right now, but they're going to change to 32. I just found out this morning. So like they represent them as like these 40 hexadecimal characters. Now they're going to be like 64 hexadecimal characters. So like whenever you create an object in SWE, you get an address. And when you publish a module is just an immutable object. So like, yeah, so you have so first of all, you have your location where this is going to be, you don't know until it's published what location you're going to get. You can't just pick like a number. It's like assigned to you as by SWE randomly, and that's part of the security model. But yeah, so like you have a location and then you have a module name. So at the top we're declaring our module, and then down below we're declaring imports. So right now I'm just importing from the standard library, which is std, std string self string. So I'm just importing like a string library. And then you have like use SWE object self ID. So that's like, I'm importing the object library from SWE. So those are just the imports at the top. Then the next you have your struct definitions. So structs are very, very simple in SWE. You don't have any concept of interfaces or traits, unlike Rust. And structs don't have methods. They are simply passive data stores. So in this struct we're defining, because it has the abilities key, it has to have an ID. So key, every struct that you declare can have some collection of 4 abilities. And the 4 abilities are key, store, copy, and drop. So key is the first one, and that means that it can be stored at root level as a root level object. We'll kind of get into like the organization of objects in like SWE's global memory in a little bit. So that's why it's required to have like a unique identifier as its first field, because otherwise it needs that. Then we just define some other fields. I had like an event name, string, duration, U64, bool. Then next you can define some like constants. And you don't have to define everything in this order. And some of the examples we'll go through, they're not going to be defined in this order necessarily. But this is like the logical order that you'll see like 90% of move modules defined in. And then you define your functions. And the functions simply accept objects, and then they modify the objects, destroy the objects, create the objects, return objects, etc. I have a bit of a cold. Then the other thing you need to know about is the move.toml file. If you guys are familiar with who's Rust developers in here? Anybody? Yeah, okay, cool. Cargo.toml, right? It's like the exact same thing, right? You got your package, dependencies, and like this is new to addresses is different. That's like the address of like your dependencies. So like for SWE examples, this is the module that I published. That's the address that it got published to. So if anybody imports it from it as a dependency, it'll see that like, okay, well, the address that I should go to is 10.772, whatever. That's the address where you can find it. Let's see. Yeah, I guess I already said that. So to explain about what's going on a little bit behind the scenes of the Move virtual machine, all the Move code that you write is compiled down into a bytecode, and then it runs on its own virtual machine called the Move virtual machine, and it's a stack-based machine. And there's the security models of Move are that there's a couple rules that the execution environment ensures. They're like invariants that it enforces, and this is what makes things secure. So only the declaring module can declare or can create or delete instantiations of one of its structs. So if I create a module that is like coin, and like I declare a struct called coin, or like let's say an NFT, only my module can create that NFT object or destroy that NFT object, and that prevents other people from like duplicating it unfairly. And like you can always tell like where a object came from. If you inspect an object, if I can go to my SWE Explorer, this is like the SWE Live Explorer. It's just explorer.swe.io if anybody wants to go there. But like if you go and look at an object, you can always see the type from where it came from. It'll have the package ID, the module ID, and the struct name, so you know exactly where it came from. So if somebody else makes another module called NFT, any program will tell that, like, because the package ID will be different. Just because they're using the same name as me, the same struct name, it's clearly a different resource entirely. The next security property is that only the declaring module can like read and write to the struct fields. So if you have like fields, if we go back to this this event name, this BUIDL week event struct that I created, it has a BUIDLweek.event name, right? Only the module that declared it can modify or read that field. So it's up to the module to declare its own structs, and then also to build an interface from which its structs can be read and write from. So that's part of the security model. Oh, I put a little note, oracles can charge fees. So that's kind of interesting. So how would you implement an oracle in Sui or in Move? Is what you would do is you would have some external service that is constantly publishing a stream of objects. And then let's suppose like it's the price of Tesla. So you have it's constantly publishing the price of Tesla. It'll just be something like Tesla price, and then inside it'll just be a U64, and that's its price. I'm constantly publishing these objects. All somebody else would have to do to access that is they would find one of the latest values of that price. They would pull it into their execution environment as an argument into a function. And then after that, they would call into my function to return the price dot price value. And because only I can reveal that dot price, I could charge you as my function input to read it. I could be like, okay, pay me like a few little sweet coins, like a fraction of a penny, in order to read this. So that's kind of cool in that it gives oracles more of an on-chain pricing if they want to use those prices atomically. So also in Move, let's see, there's no methods. Oh, the weirdest part is that there's no dynamic dispatch. And by dynamic dispatch, that prevents reentrancy. So like if I am calling into another function, I have to declare it up top as a, maybe if I go into VS Code, I can write some stuff that might help. So like if I want to call into another function, like I have to know what the other function is, but at compile time from before I'm allowed to call into it. So that means you can't simply pass in functions as arguments. There's no notion of like closure functions or anonymous functions, if you guys are familiar with those from like Rust or JavaScript, etc. All your functions are explicitly defined and then imported and then built at and then included at compile time. And so that allows a much greater level of safety statically. More of a static safety mechanism. And I think that's really what Move is trying to accomplish. Let's see. Yeah, it prevents reentrancy. Yeah, like I said, there's no interfaces, there's no traits. Sam Blackshear, who's the CTO, so he has a saying that like if code is law, then interfaces are a crime. And then static analyzable as much as possible. Like if your code can compile, it should hopefully be mostly secure. So in Sui, all functions are pure functions in the sense that if you import, if a function can only operate on its arguments, it cannot have any side effects. So like in Diem, so Aptos, does anybody know what Aptos is? Okay, yeah, Aptos is a fork of Diem. So like in the Diem and Aptos world, they have these operators called like varl global. And so that allows functions are not pure in the sense that they can reach into global memory and they can grab objects and modify them, which is kind of cool, but it also presents risks in the sense that modules could be doing a lot more than you realize. It's very easy to understand what a function can do from a security point of view if all it can do is modify its arguments, right? So like if I'm calling into another function and I'm giving it a coin, the worst it can do is like steal that coin or like modify that thing somehow. Yeah, it would be like public entry, something. Like, and then we could pass it in a coin. And like it can only operate on this coin right here. I have like, let's see. Yeah, and I think that's what I want to talk about for the overview, and then I want to go over some like actual code, and we'll see if it cooperates, if I can actually like run the code. Okay, it was working last night at least. This kind of shows what I was talking about before, though. So like you can see that this is the official Sui coin because it came from the official address like 0x2, which it's truncating for some reason here. But if I made it another module called coin, which we're going to do, my coin is going to look very different from this one. Anybody can tell that I didn't create the same object. So you don't have to worry about like somebody creating fake spoof assets really. Okay, so let's go over some examples. So the first thing I was going to go over was actually the coin module. So this is the coin. So this is what I'm about to show you is a modified version of SWE's official coin module. The coin module by SWE it declares a struct right here. Yeah, we can see that. Okay. It has an ID and it has a balance. A balance is just a balance struct, which maybe we'll talk about that a little bit. And then it has key and store. So key means it can be stored at root. It can be stored at root level, and store means it can be wrapped inside of another object. So that means I could define another struct that is like coin bank, something like this, has key, and then I could place. That's actually not bad. GitHub or that Copilot. Copilot does some good stuff sometimes. You could have a vector of coins, for example, or just like a coin. So that means, store means that I can take a coin and then place it inside of another struct. So coin bank, because I didn't give it store, I in fact can't place it inside of another struct. And so these are what's called, I guess I didn't mention this. So these are what's called, they use a system called linear types. So these are what I refer to as assets as opposed to data. So in most programming languages, what you do is, I guess in every programming language, everything is essentially just data. There's no notion, there's no program unless there's no system level concept of scarcity. I'm creating this has key, and it doesn't have copy or drop. So if I create another struct like data has copy drop, like name string, something like that. So you can copy this however you want. I can make duplicates of this. I can just throw it out at the end of an execution environment. I don't have to explicitly delete it. This is like a pure data type. And if you want to store it inside something, you'd add store. So then you could put data, something like that. So this is a pure data type, whereas this is like an asset. And that's declared at very base level within Move. And that's one of the security models. And that's one of the main features, I'd say, of resource-oriented programming, in that you're not going to accidentally duplicate a coin, or you're not going to accidentally throw one out because there was a bug. The code will not compile in the first place. Yeah. So get rid of these. Okay, we're just talking about a coin. So next, so with the coin module, I should say that it has a generic here. If you guys are familiar with generics, Phantom is just a technical thing. It doesn't really matter. You can just, yeah. So coin T. So that means that this is essentially a template for defining more concrete types. You can think of this as an abstract type, and then you could think of if I put something in here, which we're going to do, BUIDL, that would be a concrete type, right? So we're gonna get into that in a sec. So we're gonna call into, the first thing you would do if you want to create your own currency, your own type of coin, is you would call into this function, create currency. Then you present and it's going to be of type T. So this generic, you're specifying a generic. That's the type that the coin you're going to get back is. And then you have to pass in a witness. So this kind of gets into, this is idiosyncratic mostly to SWE and to Move, is sort of that they use these objects as permissions. So if you remember, I said that only the module that declares something can produce an instantiation of it. So if I'm okay, I want type T, and then I create an instance of type T, that means that the call must have originated from the person from the module that creates type T. So it's a way of kind of ensuring who is calling into this, right? Okay, so then the next argument we have is transaction context. This is specific to SWE as well. This is it contains things like who the signer is. It contains information about how many objects were created. Remember that every function is a pure function, so it has no idea what is going on outside of it. So like you need to pass in, everything needs to be an explicit argument. So you need to pass in like that's why we invented the transaction context in the first place, to let it know like who the sender is, etc., for example. So what this function is doing is create currency, right? We're calling into it, and then it's creating a treasury cap. Now it's packing this struct right here, and it can pack this struct because it declared it, right? It's declaring it right up here. And this treasury cap is cap not in the sense of a hat, but cap as in short for capability. So also another part of SWI's fundamental security model is capabilities. So they're objects that allow you to do something. You can think of them as like a badge that you pass around. So like first you have your ID, like it gets a root level stored object, so it needs an ID, and you need to pass in execution context so that it can add that new object to the execution context. And then you have like a total supply, creating balance. Let's see, creating supply. That's something. That's a balance specific concept. But basically, this treasury cap, in addition to allowing you the capability to mint and burn new coin T of this type, it also tracks the total balance that has been created. So, like every time you destroy every time you create or destroy coins, this like total supply will be updated. So, for example, okay, we have mint right here. So, like in the mint function, you present the cap, the treasury cap right here, and then you have the amount of value you want to mint, and then the transaction context again. And so what it does is, yeah, okay. So what it does is it creates a coin, and like it's kind of implicit that it's a type T, I guess right here. It's not explicitly stating that, right? And then it's creating a new object ID, and then it's like putting a balance in there. At the same time, it's putting a balance while also increasing it. Yeah. Let's see, balance, increase supply. Yeah, this is a little complicated, so I can unpack this like a little bit. So it's calling in. So it's going to set this struct. You have this field inside your struct inside the coin called balance, right? And it's going to create a balance. But how it's going to do that is it's calling into the balance module. So there's a module called balance, and then there is a function called increase supply. If you guys are familiar with Rust syntax, this is like how Rust works. So it's calling into balance, increase supply, and then it's passing a mutable reference to the treasury cap that we passed in, dot total supply. And remember, because we declared this treasury cap in here, we can just directly access its field total supply. Another module wouldn't be able to do that. They would have to call us first, essentially. So struct uses, I can't remember, what is this called? Where you have to explicitly pass specified references versus mutable references, etc. It's like a Rust concept. Yeah, but it's annoying in that like I'm always getting them wrong, but it's like helpful in that it's very explicit what's going on. You know, like if you didn't have this and mute thing, it's kind of like this would be an implicit copy. This would be like implicitly like this. Like I'm taking this and copy it, which this might not be a copyable value. So like, don't do that. So that's how when you're minting it, that's how the mint function works. Worth mentioning also is like a spec. So move also has the ability to specify what functions should be able to do. So there's an additional piece built into the move virtual machine called the move prover. And the move prover essentially allows you to specify invariants and then prove that those invariants are true. Let's see, in this case, I'm not very good at this, but I think in this case it's specifying, okay, it's specifying that it must abort if there's an overflow. So these are like other safety sort of measures that Move has. You don't need to worry about underflows or overflows and things like that. Like the transaction will abort if like something bad happens. You don't have to like worry about catching it specifically. The runtime will take care of that for you. Let's see. I want to talk about burn. Now burn is the exact opposite, right? Okay, so if I want to destroy a coin, I pass the coin in, I'm passing it in not by reference, I'm passing it in by value. And then I'm also passing in the treasury cap by mutable reference. So it's taking the coin and it's doing the reverse of packing it. Instead of packing a struct, it's like unpacking the struct. So it's like let coin equals ID balance C. So ID is not, that is a globally unique identifier. And it has to be, you can't just drop it by accident, right? If I declare some function, if I declare some variable like let x equals 3, you know, like this at the end of this execution will be like this value will be thrown out at the end of this execution. That's what I mean by dropped. And that's fine because this is just a U64 in this case, implicitly. Because U64s can be dropped. But object ID, like I said, is an asset. And so we don't want you to accidentally like throw that out. That's valuable. So that's why we have to call into another module here and explicitly delete it. So this is the SWE object module. We're calling into the object module. We're calling it the delete function inside of it. We're passing it the ID. And like because the object module is the one that creates unique IDs, it's the only module that can delete them. Let's see. Then we decrease the supply by the specified amount, and then that's burned. And then we also have like some specifications as well. You can see abort. So if the before supply is less than, yeah, I don't know. That'll help with the mood prover. So it's sort of like, you could think of specifications as the opposite of unit tests. In a unit test, you can find bugs, but you can't prove that there are no bugs. Whereas when you specify, with specifications, you can prove that there are no bugs. Yeah. At least according to whatever invariance you specify. Okay, so I think I went over that module well enough as it is. Let's see. So I created for this example, I created we're going to instantiate it. We're going to instantiate it with our own type called BUIDL. I think it's a funny word, so I want to use it as much as I can. But yeah, we're going to make a BUIDL coin. So we're declaring our own struct right here. So like I said, if you guys remember witnesses, so we created a witness type called BUIDL, which has type dropped. And only we can create this BUIDL type, right? Because we're the one declaring it. So that's like, that's a whole like security thing behind it. So normally you would not do this. I created a general function that is called create currency. That's not how you should create a currency. What you would actually do with create currency is you would do something more like this, is you would have like an init function. So SWE has this, they have this reserved name for functions called init, and they have to be private. I should also say, I should mention these modifiers as well. Fun means I'm declaring a function. Entry means that this is an entry function in that it can be called by an external client. And then public means that other external modules can call it. So so if I went like this, that means that this could only be called from a client. So this would be like the root level call I'd call into, and other functions wouldn't, and other modules wouldn't be able to call into this. And then you have I could do like public, which means that I can't call into it directly. It's not like an entry level function, but like I can create another module that does call into it. Does that make sense? I suppose a little bit. It'll probably make a little more sense in a little bit. But yeah, this is a private function in the sense that it will only ever be run once, and this is a reserved name in it. So when I publish this package, this would be run. And what I would get is like a special type of witness, and then I would call in and create this currency, etc. We'll go over that in a sec. But okay, so I created this special function called create currency. Let's try running that actually. Let's see, like God willing. So I created this script. So I'm going to cd into my client folder, and then I'm going to run yarn start create currency. Let's see if it works. I think like half the time I do this stuff, it's going to fail, so just expect it. So I created a script, if you guys run this, that generates key pairs and then requests airdrops. Yeah, Yeah, so it loaded my key pair, and it's running very slowly. If it's going to be this slow, we're probably not going to do anything live. Wow. Okay, well, so when you create a currency, what I'm doing is I'm calling into the coin module that I showed you earlier. This is the coin module. And then this is, let's zoom in a little bit so you can see this. And then we're calling the create currency function. And then we're constructing. This is how you construct a witness. It's an empty struct, so like we don't have to put anything in there. Then we're passing the transaction context, and then we're getting back this treasury cap. Okay, it looks like it did work. Weird. Wonder why that's. I think DevNet's probably fucked right now, because this was working pretty well last night actually.
The upload speed on the Wi-Fi here is pretty awful.
Maybe. Yeah, I expected it, because like whenever you try to do a live demo, it never works that well.
Unless you pay the demo guys first.
Yeah. Well, that's fine. I'll just explain like what it did. It'd be cool if I could see the results actually in the Explorer. I don't know if did you guys see that Solana went down like again yesterday?
Yeah.
Yeah.
Are they still down?
I don't know. Let's see. Explorer.solana.com. Let's see. Yeah. It looks like it's still down. Does anybody know how long they've been down for?
I saw like 3 a.m. They were tweeting about it.
Yeah.
So.
Damn. I guess that's a mass forking event is what I saw.
Yeah.
But yeah, so whenever that loads. Let's go back to showing some examples. So we construct our witness, CTX, when we get back our treasury cap. So this allows us to create stuff. So now we're going to call into the transfer module. So this is really nice because like everything is just an object. We can act on it very abstractly, right? So SWE has a general function or a general module called transfer. So we call it to transfer, and we call into the transfer function within the transfer module, and then we're passing the treasury cap by value, and then we're sending it to whoever like called into this transaction. So whoever called into the create currency transaction, they're the ones who are going to get the treasury cap. So this allows them to create more of that coin in the future. So that's an object that they possess. I suppose I should also talk about SWE's notion of objects. Objects can be in one of three states. Every object that I'm dealing with right now is an owned object, in the sense that only the reader and writer, the only person who can present that as an argument, the only person who can present that object as an argument to a function is the owner of that object. So let's see. Yeah. So like our next function we're going to talk about is like mint and send. So I have the treasury cap. Like I owned it in my account, right? So like I'm the only person who can call this because like it's an owned object. So like most of SWE, if you can obtain a reference to an object, it's mostly it's assumed that you have the right to use that object. Like possession is the same as like ownership. So like and that's not necessarily the case for shared objects. So there, in addition to owned objects, there's shared objects, and shared objects allow other people to obtain references to them and use them and supply them as arguments. So I'm going to go down and show like an example of that. Let's see. Yeah, in this one, yeah, we'll get that a little later. Yeah. Okay, so in mint and send, I'm passing in an address, which is like who I want to send the money to, and then I'm passing in a mutable reference to the treasury cap. Yeah. Then I call into the coin mint, pass in the treasury cap. I'm specifying 100 million right here, and then I'm getting back this coin. I'm getting back this coin object, and then I'm transferring to the recipient specified address. So At this time, I also want to mention that in SWE, everything is an object. And so when you have, so you can have multiple coin objects at the same time. If you look in this Explorer, this is my account right here, or the demo account I'm using at least. You can see that I have actually 5 SWE coin objects. And they each have a balance of 0.01, right? And they all have unique object IDs. So this is kind of like a very different model. Are you guys familiar with like Bitcoin UTXO in like a sense? In that like Bitcoin UTXO, you have, it's not like, everything is sort of non-fungible. So SWE chose to make this decision because they wanted mass parallel execution. So if I have, let's suppose like it was more like Ethereum, and like I have one balance object. I have one balance object from which everything draws. In that case, if I'm doing like, let's say 10 operations on it, those all need to be done sequentially in the sense that first one modifies the balance, then the next one, then the next one, then the next one. Whereas if I have like 10 separate coins, those I can send 10 separate coins to 10 separate people in parallel within the execution environment. Because those 10 transactions are no longer dependent upon each other. So that's why this is probably one of the most confusing parts about SWE for people at first. And like it's kind of been a perennial challenge that I think it'll be solved before mainnet. Mainnet probably is in June. That's what I'm banking on right now. But one problem is that I've run into continually is that let's suppose you want to buy something that's like 0.02 SWE, and I have like 5 SWE coins, and each one of them is 0.01. Like the clients that I've seen are pretty dumb, and they'll be like, "You don't have enough money for this. Your coin's not big enough for this." But it's like, no, I have enough money for it. You just need to combine them together. So like, what a smart client would do is it would grab 2 of your coins, combine them to the required balance, and then send it. That's going to be coming soon. But yeah, so that's why you should think of every, even fungible, quote, fungible coins, you should think of them as objects individually. And for those of you who aren't familiar with UTXOs for Bitcoin, so the way balances work on Ethereum is that you have like a number. It's like a bank account like you expect. Like I have like $100, I withdraw 50, put in another 20, and it's just a single balance you're modifying. That is not how it works at all in Bitcoin with UTXOs. You actually have an address with a corresponding key pair used to like unlock it. So like that's why to illustrate the difference. Suppose you had like let's suppose you had a bank account balance of $1,000, and like I hacked some protocol and like I airdropped you $100. Now you have $1,100 inside your balance. Because on Ethereum or check accounts, that balance is all like mixed together. Like there's no notion of this is the $100 that's stolen and this is the 1,000 that I owned, right? Whereas on Bitcoin or SWE, if you had like $1,000 in coin and I stole 100 and sent it to you, that 100 would have a unique object ID. So that's why in Bitcoin and SWE will probably inherit this. You can have like blacklisted coins essentially, where it's like, okay, this coin is naughty. I shouldn't be seeing you use this. Otherwise, if you use that, I'm going to be suspending your account. You know, like you try to import a certain blacklisted Bitcoin into a centralized exchange like Coinbase. They'll freeze it. So that's like actually really interesting. Let's see. Okay, back to this. Can I show I think our transaction worked. Is it even showing my latest transactions? So my last transaction says 10 hours ago. This is not true. Okay, yeah, I don't think the live demo part's going to work at all. So yeah, we have mint and send. Oh yeah, you have this notion of splitting things too. So like I was just saying, you could take a coin object, you could split it, you could merge it. I suppose that's not super interesting. Let's get into like the more interesting part, which was like I was talking about shared objects, right? Okay, so I'm going to create this new struct called shared balance, right? And like I said, like before, it has the ID, and because this is going to be a shared object, obtaining a reference to it does not necessarily mean that you own it. I'm going to create my own concept of ownership, my own idiosyncratic concept of ownership by attaching this owner field to it. Then we're going to put in some balance. It's going to hold balance BUIDL. This is in contrast to like balance T. It's not going to. It's designed only to hold BUIDLs. It's not designed to hold any sort of T you want. Let me show that ownership check right down here. So yeah, so when you, we'll talk about it. We'll get to that in a sec. Yeah. So first, let's just create it. So we're going to create a shared balance. We pack the struct like you expect. We set the owner to the transaction sender. We create a new object ID from the object module. If you remember, all UIDs originate from the object module. Remember we had to call in to delete it. And we're just creating a new balance. But now this is an interesting part. Is like we're calling the transfer module, and then instead of calling transfer, we're calling share, this share object method. And so we're taking this shared object that we created, this shared balance we created, and then we're sharing it. So that means that instead of me taking ownership of it, now anyone can reference this in a transaction. So that's why when we go down here, that's why we have a check. We have an ownership check right here. So Sweet under the hood for all owned objects is doing that for us essentially, but now we have to do it like pretty explicitly, right? Okay, so what we're doing is we're asserting that the transaction sender is equal to the shared balance.owner. So remember how we set the owner field? We're just making sure that that's us. And if not, well, then we throw this error code right here. So the idea for this shared budget thing that we're doing is that I can create this struct that essentially stores a balance, and then it's shared, and then I'm going to issue budgets to it. So like a budget is like another object that gives you permission to withdraw from the balance. And because I'm the owner, I am the only one who is allowed to create these budget objects, right? So I create this shared balance, or rather, we're passing in the shared balance by mutable reference, which anybody can do. And then we're specifying the amount of the budget to issue, specifying who we're going to send that to, and then we're asserting that the sender is the owner of the shared balance, so that I'm the one who can produce the budget. Then I'm producing a budget object. So I'm specifying like a spending limit. So in this imaginary sort of example, you can imagine that I put my coin into this shared checking account, and now I'm allowing, and now I'm like issuing, let's say Netflix, the ability to withdraw from it. And I'm saying you could withdraw up to, let's say 100 of my coins, my BUIDL coins. And then I'm transferring that to, let's say it's Netflix's address. So now Netflix will now have this budget object. And they can, when they want to redeem it, they can later go back to this function now, and they would redeem budget. So what they would do is they would pass in the budget, they pass in the shared object, the shared balance, which anybody can do, amount, that's the amount they want to take, and then where they want to send it. Now I'm doing some assert checks too. So I'm asserting that the spending limit is greater than the amount. So that's like, you can't withdraw more money. I'm specifying that you can't withdraw more money than you were allocated, right? That's important. And then I'm specifying also that the balance is sufficient to allow you to withdraw that amount. I don't really need to have this second assert in here, because like if I still didn't have this, like this is going to fail down here when I try to do this balance split. Like that's going to result. Let's suppose suppose the value of this is 100 and I'm trying to withdraw 200. Like this is the balance module is going to abort. So I don't really need that assert, but I put that in there to make it like a little more explicit. And like as a good principle, you want to abort as quickly as possible, because like if something's going to go wrong, you want to abort as quickly as possible. And that's because the user will pay for gas up until the abort point. So if you have this really long transaction that's really involved, you want to like do all the checks up front so that like they won't lose a bunch of gas it's not. I mean, SWE, gas should be very cheap, but you still don't want to waste their money unnecessarily. So like we're decreasing the spending limit, and then we're essentially just creating a coin, and then sending it to who we want. And that's kind of like this sort of like budget rebilling model. And yeah, it's not finding my transactions. This is a little disappointing because I wanted to run these live. I suppose I could show you more from even if it doesn't run, I suppose I can show you from like the client side of things, how it looks. Let's see. Yeah, I'll try to show you that. This is like TypeScript up here. So if you want to, run a transaction, it's like pretty easy to do actually. So what I'm doing is I'm passing in a signer. I constructed this earlier. So a signer is a combination of a JSON RPC provider and then a key pair. So we could probably show that a little bit. This is getting into the TypeScript SDK part. Where did I get signer? Yeah. I suppose that doesn't matter that much. Bless you. Yeah. So I'm passing in a signer. I'm passing in the function name that I want to call, and then the arguments. So it's pretty simple. It's like I just do signer.execute move call. This is all TypeScript, by the way. I'm specifying the package ID. That's the location where the package was published. So in this case, BUIDL, where BUIDL was published. And you can find that if I go to my move.toml file, you can see that I published it to this address right here. I didn't choose that address. That was assigned to me. So by the SWE runtime. So going back here, you specify the object ID, you specify the module name, which was BUIDL, a function name, which I suppose we're calling mint. It would be like mint and send. Type arguments. That's if there's generics. We don't need to worry about that. Then the arguments and gas budget, and you get a result. You await it and get a result. So it's pretty simple to submit transactions. Let me try to run it again, see if this does anything. I think this is going to be a little shorter than I wanted. Yeah, so that's pretty much what I wanted to cover for like the workshop portions of it. If you guys want to work on it on your own, what you would do is you would run through each of the commands that I had specified. So I have a create currencies command, a mint and send command, split and send, create shared balance, issue budget, redeem budget. Yeah. Like everything we just went through. Like next, I could talk a little bit about consensus if you guys want in SWE. SWE has like it didn't work. Object created. BUIDL. Where is it? Is it going to show up in my Explorer? Does anybody have any questions or anything they want to ask about? Yeah, go for it.
So I've done a little bit of like move development. I was like, as a developer, I was interested in hearing more about why like the decision to not use interfaces was made. I know you kind of made a joke about it, but I was like, it's kind of annoying. At least like.
Yeah, so like I think that interfaces are very helpful, and I kind of wish they would exist.
Yeah.
So like an interface, let's suppose. You're passing in an object and you're like, oh, this implements this trait, like display. I think that they don't want you to execute unknown code is like what the main thing that they're trying to prevent you from doing is. So like, let's suppose it implements display and you're like, okay, this implements the display method. And then I call display, but they might pass me in an object that does something I don't expect it to do. But like, because all functions are pure functions, that shouldn't really matter in my opinion, right? Because like it's not like it can access state. It shouldn't be able to access. No, it can't access my state. Yeah, their states are isolated. They're not like closures.
But if you,
Yeah.
I guess the other thing
Yeah.
too is like, at least on Aptos, you can like upgrade to modules. So it's like, you compile against the API that the other module provides, but they can still change your implementation details whenever they want.
Oh, you're talking about like the upgrade?
Yeah.
So Aptos, the way they do upgrades is you can do arbitrary upgrades or compatible upgrades, right? Which allows you to simply overwrite your module. And I think that upgrading modules is like a pretty terrible idea to begin with.
Right.
The plan for Sui is that every object will be immutable. And then if you wanted to like release a change to it, what you do is you do a migration. So you release like a new version, and then that new version you would be able to migrate assets that you created previously over. And I think it would be opt-in the sense that like if I own a bunch of objects that I created from your first package that maybe is glitched, you obviously can't take them from me because like I own them in my account, so like even if you deploy a new package, like I have to voluntarily kind of give them to you. Whereas in Aptos, they don't have the notion of owned objects versus shared objects. Aptos's programming model is more based around the modules being supreme. So like the modules are like kings of their own things they create.
Right.
So like essentially a module just creates stuff and then it stores it at addresses and it says you own it, but you only own it insofar as the module says you own it. So like I could create this module that's like, I create all these coins and then like I store the coins in your location, but then I create another function that just lets anybody sort of like just yank them right out and like steal them and stuff. Whereas on Sui that would not be possible, at least for owned objects. For shared objects, yes, but like, yeah. Sui has a much stronger notion of ownership.
Okay.
I could get into, if I talk about consensus, I think it'll make a little more sense. So a lot of, let's see this slideshow. Yeah, a lot of the Sui was basically built from the ground up around FastPay. So FastPay, anybody familiar with the FastPay white paper? It came out like 2021, maybe. The concept of FastPay is that you don't need consensus for certain types of objects, for certain types of transactions. So let's talk about like a shared consensus first, so like you can understand owned objects. So for shared consensus, here I'm the transaction sender. What I do is I broadcast my transaction to all of the validators, or at least a quorum of them, a 2/3 majority. And then they're going to check this, they're going to sign it, they're going to return it and be like, okay, this looks good. And then I'm going to broadcast it again. And then it's going to go through this consensus pipeline. And the consensus algorithm that Sui is using is Bullshark. So Bullshark was a white paper from 2022. And like it's like top of the line bleeding edge, like consensus stuff. And it's essentially, it's a way of ordering transactions amongst a group of machines. And then agreeing on what the results are. Sui also does not have blocks. They no longer have the notion of blocks. They simply have transactions. They have objects that modify transactions. They don't have individual blocks anymore, which I thought was pretty cool. So for an owned object, let's suppose if I am the only person who can read and write to from an object, which is like the case for an owned object, then you don't need to do a whole consensus thing. So you don't need to run it through consensus. So I can. So the way FastPay works is essentially you broadcast it to a quorum of validators, and they're like, okay, this is legitimate, and then they return their signatures. Then I collate all their signatures into a certificate. That certificate essentially says like, hey, these people all sign. These validators signed this. This is legitimate, and then I return that to the validators who are like, okay, this transaction is now finalized. So without consensus and in 2 hops, you can do an owned object flow, and so that's very fast. In DevNet previously, I was seeing like confirmation times of under like 2 or 3 seconds, and hopefully that should hold up in mainnet. DevNet has only been 4 validators that are all run internally by Miston. Testnet 2 had 40 validators that were run by random parties who applied and got accepted. But yeah, that's pretty much all I want to talk about today. Sorry I couldn't do like the live demo stuff for some reason. Deb's not cooperating with me today. But yeah, did anybody have any questions or things that they wanted to bring up about SWE or Aptos or DM or Move or anything at all? Yeah, go for it.
Sure, like last time I wrote SWE Move was before they came up with dynamic objects, and that changed a lot. So like, what's your current take personally on pros and cons or liking and disliking about how that changed stuff?
But you're talking about dynamic fields, right?
Yeah, sorry.
Okay. I really like them. So like the capsule standard that I was talking about before is mostly built around dynamic fields. So like for you guys who don't know, dynamic field is a concept unique to SWE that isn't part of Aptos, isn't part of Diem, and it allows other modules to attach. I could probably just show it. Yeah, I could just write up some examples. It allows other modules to attach their own fields to other people's objects. So you could be like public fun, attach something. Yeah, so I wonder if this will work. Probably not, but like maybe. Yeah, okay. Dynamic field add. Let's see. Oh, I need the UID. Okay, as long as I can get access to the ID. The only shitty part about dynamic fields is that every field you add is its own separate object. Key, and then I'd be like value. Yeah. So like it gets kind of expensive from the runtime. But kind of basically do something along this flow is that like you're passing in some object. I need a mutable, all I really need is a mutable reference to a UID. Let's just do that. And mute UID. Yeah. Yeah. So dynamic field add, whatever this object is, I don't even know what this object is, but I'm adding my own key and my own value to it. And it's a very powerful pattern. So like what I'm using it for capsules is like when you publish a module, you can claim a publish receipt, and then for my own modules, you pass in that publish receipt, and then I essentially add a stamp to it that's like, okay, I saw this once, and now I'm issuing you a type. Like you published this module, and I'm going to issue you a type object that says you can I'm issuing you a type object. And then I'm enforced that you can only do it once by adding a stamp to that publish receipt. So if you present that publish receipt to me again in the future, I'll see my own stamp because I'm checking for it. And like I'm like, okay, I already issued this object for you. Don't do it again. So I think that they're pretty cool. Yeah, maybe a little expensive. A little yeah. All types need to be known too, so like it'd be cooler if they were more generic. Like if I'm doing dynamic field remove, let's say my key is like a string, I have to specify the type of the value I'm getting back. Key. I'd be like let value. I have to move always has to know what every type is at compile time. There's no surprises. So like I have to specify what the value stored here is going to be, what the type of the value is that's going to be. And if I'm wrong, this is going to abort, right? Like I can't just be like, pass in whatever and, I'll just transfer it, It's not like I can, like he was saying, like interfaces. It'd be cooler, it'd be more flexible, but perhaps less secure. I suppose flexibility and security could be a little bit of a trade-off. It'd be cooler if it could be like T, T, and then we just play up here like T has keys, key store. So then I'd just be like, in this case, I'd just be like, okay, I'm specifying this generic, I'm specifying properties it has, and then I'm specifying that this value is going to conform to this sort of interface, you could call it almost an interface, and then I'm going to transfer it. And because it has key and store, like this should work, like this transfer will work, but Move won't allow me to do this. Move will just be like, if I try to run compile this, it'll be like, no, I don't know what T is. You can't do this. Can't do this to me. Yeah. Did anybody have any other questions or thoughts? Yeah, go for it.
You mentioned that like some objects don't require consensus, or some transactions don't require consensus. Like what kind of transactions would it require you to?
So anything involving a shared object needs to go through consensus. Anything involving only owned objects does not need to go through consensus. So let's suppose create currency. So like this is an example of one that wouldn't require consensus. Is because I'm just calling into this I'm calling into this other module, and I'm just getting back this treasury cap that I own, and then I'm storing it. And so like there's no chance of contention occurring here, because like there's no sort of shared resource in this entire like execution flow where somebody else could be contending for the same resource. Whereas with the shared object over here, we have this shared balance. So remember that we have this assert over here that's like, obviously you can't withdraw more than your budget, but we also can't withdraw more than exists in the balance. So like, imagine that I create this shared balance, and then there's a bunch of other people trying to withdraw money from it all at the same time, right? There's like this contention, and then you need to go through consensus, because now our transactions need to be ordered. Where it's like, okay, suppose there's like 1,000 people trying to withdraw a total of $1 million, and there's only 500,000 in it. Like anyone who gets below this certain like ordering line, it's a bank rush. This FTX bank rush. Everyone trying to get their money out of this shared contention object. Yeah, or maybe it's like an NFT mint or something like that. Yeah. So.
What about contention with yourself? Like, could you do multiple of these non-consensus transactions, and then?
So if you were to that would be called, what's that called when you equivocating? So like, as long as your first one is done, it doesn't. You can like do multiple ones sequentially, but it's sort of like, if I were to suppose I were to create 2 transactions, this would be like a deadlock scenario. It's like, suppose I had 1 coin and I signed 2 different transactions. Like one transaction I'm sending it to JP, and the other one I'm sending it to you, and then I broadcast both of them at the same time. The worst case scenario, the best case scenario would be that 2/3 majority of the validators sign off on one of them, and then it goes through, and the other one is just aborted, because it can never achieve a 2/3 majority, or can't achieve more than 1/3. So that one will be dropped. But the worst case scenario would be where one gets like 55% and one gets like 45%, and then neither of them can get to the 2/3 like majority that they need, and then you'd be like deadlocked. So like you'd have. I'm hoping they find a better way to resolve this, but you'd have effectively like fucked yourself for that object for until the end of the epoch. I think there's an epoch every day, and then like that deadlock would be like good, you know.
Interesting.
Yeah.
So just don't do that.
Don't do that, yeah. But like also that's kind of interesting. It's an interesting question in that like you are essentially moving consensus from the database layer into the application layer. You can think of it like that. It's like, suppose that I have 10 servers and they all share the same key pair, right? They might not be. They're not going to be aware. They're not going to be aware because they're operating independently. They're not aware of what the other ones are doing, so they might incidentally equivocate themselves. They're not trying to, but like they end up doing that. They're both trying to like use the same object. Like they queried the blockchain. They're like, oh, I have a balance of 1,000, but then like a second later, after they got suppose that query has like a latency of like 2 seconds or something. It's 2 seconds out of date. That money's already been spent, and like they're equivocating each other. So like I could see that being an issue in the future. I could see that being an issue. I'm not sure how you would resolve that, because like people are kind of used to databases handling the content, and if there's any contention, they're used to the database handling it. Like they don't want your application having to handle it. So yeah, in that case, if I had 10 servers all going for the same object, I would perhaps just make that object a shared object and then give them all their own keys. That would probably be better, even though like shared transactions are slightly slower and slightly more expensive, right? Which is like the point of not doing them. But like at least my application wouldn't have to worry. Like my server could just worry about its own state and not about the other 9 server states. Yeah, good question though.
Cool.
Yeah. We're getting into some edge cases. Did anybody else have any questions or thoughts and stuff? I'm kind of surprised. We managed to go like almost the full length. We could like at least we could go for another like 13 minutes. We got the room before they kick us out or something. And then there's like a 30-minute transition time between the next session. Yeah, I guess that's it then. Oh, you got a question?
No, really use cases. Can you maybe give us an example?
Oh, use cases of specifically like Suite?
Yeah.
Okay, so right now, I'm thinking of applications that people are building. So Suite is trying to orient itself mostly towards gaming, specifically like APAC gaming, Asia Pacific kind of region type gaming. And I think that Suite is useful in terms of being a database. So when I think of Suite conceptually, I think of it as replacing database. If you guys are familiar with game development, you'll have a server and like PlayFab or Unity's sort of server, and they provide like a database as a service for you. And like they also have this notion of like economic items. So like when I'm making a game, I'm issuing these virtual currencies, I'm issuing these virtual items, et cetera. Suite is better suited for that in that it like has the linear types and it's distributed, and you could have assets move between other games, et cetera. And you can attach real world financial like secondary markets to them. I think that would be pretty. I think that's mostly what they're oriented towards, and that's what I'm trying to build with capsules at least. Yeah. For other use cases, like payments, it should work pretty well for payments. But like the problem with payments is that Visa and MasterCard works really well already for most people. So there's not a big incentive for them to move over. Like people just don't really care. Let's see.
So when you say the objects, forgive me.
Oh no, you're good.
But when the objects, let's say we're talking about the ERC 721. Would that be considered an object?
So ERC 721 would be, I consider like an interface standard. So like you could have something like that. There is actually a module I think they call ERC 721 in like the Suite core. Let's see if I can find that. Okay. ERC. This is just a metadata. I haven't really looked at this, but I'd be interested in seeing that. Looks like what they're doing is that they're creating a struct called ERC 721 metadata, token ID, name, URI. It's just a link to a URL. Then what are they doing? I don't know. I've never really looked at this module. But yeah. But basically, ERC 721, you could think of it as an object. In this case, if you want to implement an NFT, the way I would do it, well, the simplest way to do it, this is the way I would do it. Is you create a struct like NFT has key store, something along these lines. Then I'd create like an ID, UID. So this is like a unique identifier for it, so it can be like globally identified. And also notice that like it has key and store and not like copy and drop. So if it had copy and drop, I could duplicate it, throw it out. Not going to do that. That's not really well. You could probably add a name, which would be like a string. We could add a URL, which would probably just be another string. I mean, keep it simple. You get a description, why not? And then I would probably do something like a public fund, make this an entry fund, mint. So if you want me to create it, no. How did you do Google Copilot? Nah, it did okay. We're just gonna return, yeah. Let's see. Google Copilot kind of sucks. Okay, never mind. So we'd probably do like let NFT equals NFT. It's trying. I think I'm going to turn it off. Honestly, Google. How do you guys feel about Google Copilot?
Copilot's great. There's just not a lot of move devs to trade it.
Yeah, exactly. Like it's giving me like Rust code. It doesn't even know what I'm making, and it's like all this syntax that doesn't exist and stuff.
800 public repos on the planet right now.
Yeah. So like, well, let's take a payment. Let's make this a little more interesting. Let's do like a coin, Suite. We didn't specify that. Okay, so and then we're gonna take. So like, cause we're so for this value we're gonna take for this function, I should say, we're going to take a coin type SWI, and then we're going to transfer the coin. I suppose we're not specifying a price, but we would probably want to specify a price. We'd be like transfer, and it'd be like whatever the project's address is. We could probably hard code that. So like this function is accepting a coin, it's transferring the coin to us, and it's creating an NFT, and then it's returning the NFT by packing the struct. And like in this case, you're specifying the name, description, URL, which you probably wouldn't want people to do that. But like, yeah, that's what this one's doing. You probably do some sort of like coin balance. I think it's like coin value. I think that's the function name. It'd be like assert, probably like assert coin value is greater than 50. Now we're not giving any refund if they give us more than 50, because we're asshats. And then we're taking the coin, and then we're going to take the coin, create the NFT, give it to them. So that would kind of be just, this isn't how you'd actually do it in production, but yeah. Does that help answer your question?
Yeah, well, actually it does.
Yeah.
If you're a little more complex, let's say we were doing ERC 1155, and we included the ERC 20.
So 1155, the main difference is that you can have like a semi-fungibility. So like that's an interesting like concept. Let's suppose we added like a quantity field. We can make it maybe like a U64, and then it would be like quantity 10. So we'd start off with a quantity of like 10, let's say, and then like suppose you're the owner of this. We'd probably want to put a max supply of this as well. So this would also involve like a sort of a shared, like here we could create 1 million of these or 1 billion of these, but like we might want some like shared like total supply remaining object. Just this is sort of like I'm just inventing these concepts on the fly, and then we assert like supply remaining. Probably be like supply remaining dot supply, something like this. Probably equals 0, and then we'd probably be like supply remaining dot supply equals supply remaining dot -1. That'd be like, yeah. Okay, so now let's get to the semi-fungibility aspect. We'd probably do like a, what would we call it? Split. So we'd probably pass in this NFT, and then probably return, let's pass it in by value, and then let's return 2 NFTs. It could be something like let new NFT, and we'd probably do quantity NFT dot quantity divided by, oh, let's do this up here. How do I do this? NFT dot quantity equals NFT dot quantity divided by 2. And now I'm just going to do NFT. So I'm not modifying it. I'm going to do NFT quantity. I have to do ID. I'm going to have to assign it a new object ID. And then what else would I do? Let's see what else we had. We had name description URL, right? And we probably like we duplicate that. Yeah, there we go. Thank you, Copilot, saving me some typing. Does that look about right? And then we'd return. This. Return NFT, new NFT, something along those lines. Does that make sense?
That's exactly what
Yeah. We could add like a quantity field, and then we'd allow it to split it. We'd probably want to be like assert NFT quantity is greater than 1 to allow it to split. Otherwise, if it's less than 1, we probably want to do that. And also, this is kind of like subject to rounding errors in a way. Like you could lose a few, which we'd probably like want to check for that rounding error added into 1. But yeah, so kind of like that. Yeah. Did you have like is that helping?
Yeah, it's helping a lot, actually.
Yeah.
And now I'm really bummed out that I got here late, but I had to register late.
Yeah, that's okay. We recorded it at least. I do have the example I went through is like a public repo. It's on our GitHub, so you can fork it and like go through it, and it'll probably work better than it did for my live demo because like DevNet's not giving me results. It's telling me that I haven't submitted a transaction in 11 hours, which is not true. If you guys go through the DevNet Explorer, it counts everything either as a coin or an NFT, and everything that isn't a sweet coin is just an NFT, which is kind of silly. So like I'll create these other objects that it's not even going to load, but I'll create these other objects that like it's an NFT. Thanks everybody for coming here today, and I'm glad we went the full hour and a half. I wasn't sure if I was going to have enough material to go an hour and a half, but yeah, thank you guys.